Rain is falling with a speed of 25 meters per second at an angle of 20 degrees to the vertical. A car is traveling along a horizontal road into the rain. The windscreen of the car makes an angle of 32 degrees with the vertical. The car is traveling at 20 meters per second. Find the angle at which the rain appears to strike the windscreen. Here is VR, the velocity of a drop of rain. It makes an angle of 20 degrees to the vertical, so we could be just talking about a single drop of rain. This is the direction it will move in, and this is the angle with the vertical. It's 20 degrees. Now we want its I and j components, so we just project across here. We can see that the j component is negative. The I component is actually positive. The I component is got by multiplying the magnitude of this vector, which is 25, by the sine of 20. So we have 25 sine 20 times I. The I component is positive, as you can see. This component is pointing to the right. The j component, however, is negative. The j component is 25 cos 20, or minus 25 cos 20. This yellow vector here represents the velocity of the car. Well, we could think of a point on the bonnet of the car. That point is moving to the right with a speed of 20 meters, moving to the left with a speed of 20 meters per second. Because it's moving to the left, the velocity vector is minus 20i. There is no j component. We are going to be interested in the velocity of the rain relative to the car, or if you like, well, in the first case we're going to be interested in the velocity of the rain relative to a point on, say, the bonnet of the car. We'll worry about the windscreen later. It's only a matter of adding on an angle actually, but let's say this point here, we'll call it C. So we're interested in how the rain appears to move relative to this fixed point on the car. Relative to the ground, VR is given by 25 sine 20i minus 25 cos 20j. This is the velocity of the rain relative to the fixed ground, or an observer standing stationary on the ground. And VC is the velocity of the rain relative to a stationary observer on the ground. We want the velocity of the rain relative to a moving point on, say, the bonnet of the car. I'm calling that point C. So we use our relative velocity formula. This is the formula we discussed in previous videos. We just, to get VRC, we work out VR minus VC. We subtract these two vectors. So we take VR, which is this vector, and subtract minus 20i. So we look at the I components. We take the I component of VR, which is 25 sine 20, and subtract the I component of VC, which is minus 20. So we have 25 sine 20 minus minus 20. That gives 25 sine 20 plus 20 times I. Then we take the j component of R and subtract the j component of C. The j component of R is minus 25 cos 20. The j component of C is 0. So we just have minus 25 cos 20. If this is confusing, you could just think of a single drop of rain. So VR refers to the velocity of a single drop of rain. And we have the velocity of that drop of rain relative to the car is given by this here. Working this out, we get 28.55i minus 23.49j. Now the question is, what angle does this raindrop appear to make as it approaches the bonnet of the car for a point C moving with the car? Of course, if the car was stationary, then the angle would be straightforward. We could just work it out from this diagram here. We see that VR makes an angle of 20 degrees with the vertical. So this angle down here would be the angle that we would be after. This angle would actually be, let's see now, the three angles add up to 180. So this angle would be 70 degrees. But it's not going to be 70 degrees in this case, for the case of a point moving with the car. It'll be a different angle. find that angle, we take the j component and divide by the I component. Let's look at the point C. The point C, of course, is moving to the left. A raindrop comes in, strikes the point C. Its velocity is given by this vector here. Let's show this velocity vector on this diagram. So this is the x-axis, this is the y-axis. Actually, this is a moving axis. We could call it x dash y dash if you like, to indicate that we're talking about a moving axis. We could show this vector. Its I component is positive, its j component is negative, so it looks like this. So a raindrop is coming in, and it appears to be moving with this velocity. So I'm showing the velocity vector with the origin at C. So the raindrop is shown just before striking point C, or its velocity vector, I should say, is shown just before the drop strikes point C. So we have its components. So what we need to do is find the angle it makes with the horizontal. Well, that's this angle here, or same thing is this angle here. So as I said earlier, we divide the components. This component here has length 23.49 and this component has length 28.55. So the tan of theta is opposite over adjacent. So theta is inverse tan 23.49 over 28.55. Working this out, we get 39.45 degrees. Now we are interested in the angle at which the rain appears to strike the windscreen. So let's just look at the diagram. So we've shown now that a drop of rain from the point of view of a moving point on, say, the bonnet of the car makes an angle of 39.45 degrees. So we want the angle of this trajectory of the raindrop with the windscreen. The angle between this trajectory and the windscreen. So let's just draw in the windscreen. Let's just draw it in here. So I'll do the trajectory of the raindrop in blue. As for the windscreen, we know that there's an angle of 32 degrees between the windscreen and the vertical. So this line here is the vertical, which means we've a right angle triangle formed here, and this angle here is also 32 degrees. These are vertically opposite angles. So this angle here can be calculated by the fact that these three angles add up to 90 degrees. So we just take 32 from 90. We get 58 degrees, and now finally we can get the required angle, which is this angle here, because these three angles add up to 180. So you get an answer of 82.55 degrees.